Exponential functions with base e. In order to derive the value of e, let's focus in on a portion of our compound interest formula. We begin with a equals p times 1 plus r over n to the nt power. Specifically looking at just 1 year, let t equal 1. So that gives us 1 plus r over n to the nth power. Now using the special case of r equals 1, we have 1 plus 1 over n to the nth power. Does this approach a number as n gets very large? Use your calculator to complete this table. When n is 1, this will equal 2. When n is 10, it becomes 2.5937, and as n becomes very large, it gets closer and closer to this number here, 2.7182. Mathematicians proved that as n approaches infinity, 1 plus 1 over n to the n power approaches the number they were to name e. E is an irrational number. Its decimals go on forever and never end, repeat, or form a pattern. Its first few digits are 2.7182. Here are the first 1,000 digits of e, but e has been calculated to millions of digits. Your calculator actually has a key for e since it has many uses. E shows up in a wide range of math, science, business, economics, medicine, etc. It was first used but not identified specifically by John Napier in about 1618. It was derived by Jacob Bernoulli and then used by Leibniz and Huygens in the late 1600s. The designation of the letter E for this number was made by Euler in the early 1700s. It was first computed from solving the compound interest problem. Since then, it has been computed many different ways. The letter E allows us to simplify the continuous compounding of interest, n going to infinity, by replacing this formula with this formula. A equals p times e to the RT power. A is the amount after t time periods, p is the principal or starting amount, r is the growth rate per time period, and t is the number of time periods. Tariq deposited $1,000 into an account that earns 10% interest compounded continuously. How much money will he have in his account after 3 years? Here's the equation we're going to be using for continuous compounding. A equals p times e to the RT. The principal is $1,000, r is 10% or 0.1, and it's 3 years, so t is 3. Put this in your calculator and you will get $1,349.86. The account balance after 3 years of being compounded continuously is $1,349.86. The natural exponential function is the exponential function f of x equals e to the x, where e is the base of the exponent. It is often referred to as the exponential function. So here we have a domain of all real numbers, a range that goes from 0 to positive infinity, not including 0. The y-intercept is right here at 0, 1, and it goes uphill from left to right. Since the value of e is between 2 and 3, the graph of f of x equals e to the x lies between the graphs of g of x equals 2 to the x and h of x equals 3 to the x. So here in purple we have 2 to the x, in black we have e to the x, and in red we have 3 to the x. Evaluate each expression to the 5th decimal place. You can just plug these into your calculator to evaluate them. E to the negative 3 power is 0.04979. E squared is about equal to 7.38906. E raised to the pi power, so this is 2.718 raised to 3.1415, is about equal to 23.14069. And then we have e to the 5.3 power equal to about 200.33681. Sketch the graphs of f of x equals e to the x and g of x equals negative 2 times e to the x. Compare the domain, range, y-intercept, and asymptote of each function. Determine any transformations required to get from f of x to g of x. Here in black we have f of x equals e to the x. The domain is all real numbers. The range is from 0 to positive infinity. The y-intercept is 0, 1. The asymptote is the x-axis at y equals 0. Here, in purple, we have negative 2 times e to the x. The domain is still all real numbers. The range is from 0 down to negative infinity. The y-intercept is here at 0, -2, but the asymptote is still the x-axis at y equals 0. The transformation between f of x and g of x is a vertical stretch with a factor of 2 and a reflection across the x-axis.